Hey everyone, did you know that right now, no matter what you're doing, you're being pushed on and squeezed by a totally invisible force? It's happening constantly. So today, we're going to pull back the curtain on that force, make it visible, and really get a handle on how it all works. Okay, so here's a puzzle for you. Think about a tire gauge, right? It might read something like 40 psi. Then you've got a blood pressure monitor, and that might say 120 millimeters of mercury. I mean, they seem totally different, don't they? One's for your car, one's for your body, completely different units. But what if I told you they're both talking about the exact same physical thing? Yep, you guessed it. They're both measuring this thing called fluid pressure. It's this constant, invisible force that's being exerted by all the fluids around us and even the fluids inside of us, which, when you think about it, is kind of wild. So the big question is, how does this invisible push actually work? All right, here's our game plan. We're going to start super small, at the microscopic level, to find out where this push even comes from. Then we'll zoom out to look at force, area, and direction. After that, we'll tackle the absolutely crushing weight of the air, seriously, and see what happens when we dive deeper. And finally, we'll circle all the way back to crack the code on how we measure it in the real world. Okay, first things first. What even is fluid pressure? Where does it come from? Well, it all kicks off with this constant, chaotic dance of molecules all around us. So just picture the air in the room you're in right now. It feels like nothing, right? But it's actually packed with countless tiny molecules, all zipping around like crazy. And they're constantly bumping into every single surface, your skin, the walls, everything. Now, each one of these little collisions is just a teeny tiny push. You'd never feel just one. But when you have billions and billions of them hitting a surface every single second, well, all those tiny pushes add up to a real continuous force. And here's the cool part. It's all proportional. If you have a bigger surface, you get more collisions, which means you get more force. Simple as that. And this right here is the absolute key to understanding pressure. Since the total force grows perfectly in step with the area, that ratio, the force per unit of area, always stays the same for a fluid that isn't moving. And that constant value, that force divided by the area it's pushing on, that's what we call pressure. Okay, so we've got the basic idea down. Pressure is all about force spread out over an area. But there's another piece to this puzzle, a really important detail we can't ignore, the direction of that push. First, let's talk about a more general term, which is stress. In physics, stress is just force over an area. It's a broad category. But as you're about to see, pressure is a really unique, really specific type of stress. And here it is. This is what makes pressure so special. That force from a fluid doesn't just push at any old angle. Nope. It always pushes perpendicular to the surface, straight in, at a perfect 90-degree angle. Think about it. All those little molecules bouncing off a wall, the net effect of all those collisions is a push directly into that wall. Now, this might sound a bit counterintuitive. You might be thinking, wait a minute, if pressure comes from force and force has a direction, shouldn't pressure be a vector? It's a great question, but think of it this way. Imagine a single tiny point deep in the ocean. That point is being squeezed from all directions at once, from above, below, left, right, front, back, equally. Because there isn't one single direction the push is coming from, we don't need a vector. We just need a single number, a magnitude, to say how intense that squeeze is. And that's why pressure is a scalar. All right, so we've established that the air around us is constantly pushing on us from all sides. But just how big of a push are we talking about here? Let me tell you, the answer is probably going to shock you. It's a lot. Get ready for this. The pressure from our atmosphere down here at sea level is about 100,000 pascals. Now, a pascal is a newton of force on a square meter. So what that means is, for every square meter of your body, the air is pushing on you with a force of 100,000 newtons. To put that in perspective, that's like having a city bus parked on top of you. So, that leads to a pretty obvious question, right? If there's the weight of a bus pushing on me right now, why am I not a pancake? Why don't we all just get crushed? The answer, in a word, is balance. It's because the fluids and air inside our bodies are pushing outward with that exact same force. So the massive push from the outside is perfectly canceled out by the push from the inside. It's a perfect equilibrium. You've seen this in action, maybe without realizing it. Think of an empty plastic bag. It just sits there, right? Air inside pushes out, air outside pushes in. But the second you suck the air out of it, whoosh, it collapses. That's the outside pressure winning the fight. Okay, so the pressure we feel from the air is basically from the weight of all the air piled up above us. That makes sense. But what happens if we switch from air to a much, much denser fluid, like water? The logic here is actually super intuitive. Let's break it down. When you're just at the surface of a pool, all you've got pushing down on you is the atmosphere. But as you start to go deeper, you now have a column of water right on top of your head. And that water has weight, right? That weight adds more pressure. And the deeper you go, the more water is piled on top of you, the heavier that column gets, and, you guessed it, the higher the pressure becomes. And this leads to a really cool and kind of surprising fact. The change in pressure only depends on one thing: the vertical depth. That's it. It doesn't matter if you're swimming in a huge ocean or if you're in a super narrow pipe. The pressure 10 feet down is exactly the same in both places, because in both cases, you've got 10 feet of water above you. The overall shape or size of the container, completely irrelevant. All right, we have all the puzzle pieces now. Let's put them together and finally solve that mystery from the very beginning. Let's talk about the tire gauge and the blood pressure cuff. See, it turns out there are two different ways we talk about pressure. First, there's absolute pressure. That's the whole shebang, the total true pressure, which includes the atmospheric pressure plus any extra pressure. But then there's gauge pressure, and this is what most of our everyday tools measure. They basically zero out the atmospheric pressure we're always living in and only tell you the extra pressure on top of that. And here it is. This is the solution to our puzzle. When your tire gauge says 40 psi, it's not the absolute pressure. It's telling you the pressure inside is 40 psi higher than the atmospheric pressure outside. Since the atmosphere is about 14.7 psi, the true or absolute pressure in that tire is almost 55 psi. And it's the exact same story with blood pressure. A reading of 120 millimeters of mercury means it's that much above the atmosphere's pressure. They are both measuring gauge pressure. Mystery solved. So let me leave you with one last question to chew on. We now know for a fact that pressure gets stronger the deeper you go. So think about an object submerged in water. The pressure pushing up on the bottom of that object has to be stronger than the pressure pushing down on the top of it, right? So does that difference create a net upward force? And if it does, could that be what makes things float? Something to think about.